Alrighty, well this video is going to be the second part of the chapter 3 material, so let's go right into it. So in the last video we spent quite a bit of time learning how to write chemical formulas for various compounds, for both ionic and molecular compounds, and then we also learned how to name them. What I want to start with today is talking about naming specifically a type of molecular compound called an acid. Now, we are going to be learning a lot more about acids in a later chapter, in a couple more chapters when we learn about acids and bases and acid-base reactions. But here, we really are just going to be focusing on how to name them. So if you can accomplish that, then that's perfect. Now, let me just start out by saying that you have all been assigned to memorize about 10 acids here. And that was fine to just approach it from the point of view of memorization, because these 10 are by far like the most common ones in chemistry or in general chemistry. What I'm going to teach you though here allows you to name several more that you weren't able to name before. So in addition to having some of them memorized, we also want to be able to understand the rules of how these names came to be. So let's go ahead and start taking some notes. So we're going to be talking about naming acids. And I'm not even going to attempt to explain what an acid is quite yet. Although, let me put a few of the acids on the board, and just so you can see a little bit, these are the ones that, some of the ones that you memorized. All right, so those are just 5 of the ones that were on your memorization list. What I want you to notice about all of them is that all of them have an H in the front. And in terms of the acids that you'll encounter in Chem 101, they all will have an H in the front. And not only that, I do want you to notice that these are all molecular compounds. Now, how do we know that they're molecular compounds? Hopefully you can see that all of these acids contain nonmetals down to other nonmetals, with no exception. So hydrogen, remember, is a nonmetal. And as long as all you see is nonmetal, 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 these are all molecular compounds, which basically tells you they are held together by covalent bonds. So at this point, that's enough to know about acids. Acids are going to have an H in front, and they are all going to be molecular compounds. But the naming rules are not the same as just regular old molecular compounds. You're not going to be using prefixes for acids, okay? So it's kind of a different set of naming rules. In terms of naming acids, there really are 2 types of acids, and they have different naming rules. So there's binary acids and oxyacids. All right, so let's start with binary acids. Binary acids contain hydrogen and one other atom. And right there you can see bi meaning 2, so it's just a 2-atom acid. So of the list that I have up here, hopefully you can see that there's 2 binary acids, hydrochloric acid and hydrobromic acid, okay? And I think there's a few more that you memorized, hydrofluoric and hydroiodic. All right, when it comes to naming a binary acid, these are the ones that you're going to use hydro for. These are the only ones that you're going to use hydro for. And then what you're going to do is you're going to use the base name of the nonmetal. And then you add ic acid. And that is how the binary acids were all named. So for instance, that's why he is called hydro. That the nonmetal, this is always going to be a nonmetal. Base name of the nonmetal. The next one is always a nonmetal, so hydrochlor, because of chlorine, ic acid, hydrochloric acid. Hydrobromic acid, hydrofluoric acid, hydroiodic acid. In terms of how this really helps you, in a way it doesn't, because you had already memorized those 4 very famous binary acids, but that's where really how their names came to be. So, but the oxyacids, we are going to add some stuff to your knowledge base here. So oxyacids contain hydrogen and an oxyanion. Now, an oxyanion is exactly what it sounds like. It's an anion, so it's always going to be a negatively charged, but what you're going to notice is that they're all polyatomic ions. They're polyatomic anions. It's a polyatomic ion containing oxygen. And that's why it's called oxyanion. And what you'll notice is on your list of polyatomic ions that you memorized, the vast majority were oxyanions: hypochlorite, chlorite, chlorate, perchlorate, acetate, carbonate, bicarbonate, nitrite, nitrate, phosphate. All of these are oxyanions. They're oxygen-containing polyatomic ions. So of the list that I have up here, I've got 3 oxyanions or oxyacids. Okay, you can see that. Let's see here. So how are these ones named? So to name these ones here, let me go ahead and give you what you're going to do. First of all, there's no hydro. Okay, what you're going to do is identify the polyatomic ion inside of it. So all of the oxyanions will have a polyatomic ion like embedded in it. So for instance, let's take this one here. What you have to do is recognize that there was a polyatomic ion embedded in it, and it was nitrate. So that's why having these guys memorized is so important. So this acid contained nitrate. Notice, I want you to note, maybe some of you already did, but it's something that you should notice. The number of hydrogens matches the magnitude of the charge on the polyatomic ion. Did you notice that? Maybe you did. But for instance, nitrate was a 1- charge. Notice it only has 1 hydrogen. Sulfate, SO4 2- is a 2- charge. Notice he has 2 hydrogens. What was another one? This acid here, phosphoric acid. Phosphate had a 3- charge. Did you notice that he required 3 hydrogens? So there's reasons for that, but at the end of the day, I want you to notice that the number of hydrogens matches the charge on the polyatomic ion. So first of all, note or identify the polyatomic ion that's inside of the oxyacid, and then just apply this rule here. If it ends in, it's either going to end in 8 or ite. If it ends in 8, okay, if it ends in 8, then you're just going to take its base name of the polyatomic ion and add ic acid. And that's the name of the acid. So for instance, let's do this one here. He contains nitrate. Trate ends, this is nitrate, not nitrite, nitrate. That ends in ate, okay? So we're just going to call this guy nitric acid. So you see we use ic acid as the name, nitric acid. Another example, this guy here. This contains phosphate. Phosphate ends in ate, so we're going to apply this rule here. And therefore it becomes, now, some people would say, well, why is it not phosphoric acid? A little bit of this is a historical thing, so you kind of just have to roll with it. But notice it does end in ic. It's phosphoric acid. So if the polyatomic ion ends in 8, it becomes an ic acid. This one here, did you notice that it contains perchlorate right here? So therefore we call this perchloric acid. All right? Now, if the polyatomic ion ends in, so if it ends in, this is just quotations, if it ends in ite, you're going to take its base name and you're going to add us acid. OUS acid. Let me go ahead and give you, I don't know that I have any examples, I don't, of this type. Let me put a few up here. Let's go ahead and name this compound. I don't believe he was, let me see. I don't think he was on your memorized list. He's not, but at this point we can name him. So let's do him and let's do this guy here. This is two good examples. Okay, this acid, you can see it contains a polyatomic ion, and what one is it? It's nitrite, Nitrite. So we're going to name it nitrous acid. This is nitrous acid. And this guy here, what polyatomic ion does he contain? Hopefully you have that memorized. ClO2 minus. That was chlorite. Chlorite. So therefore we're going to call him chlorous acid. Okay, so that's the naming convention of acids. Now we can go the other way. Let me just throw one more thing at you and see if you could conquer this. Now that you know the rules. So ate is ick, ite is us. How I remember that is that if I ate something disgusting, I would say ick, and that's enough. Let me just give you a name and see if you can figure out the formula. How about hypochlorous acid? Could you get the formula for that? Well, you can see us, so that means this contains the hypochlorite ion. Hypochlorite was ClO minus, so the acid must contain this. You would have one hydrogen for every charge, and so the name or the formula for the acid is HClO, and that would be hypochlorous acid. All right, so that's going to allow you to name a few more acids that are not on your memorized list. And I would definitely make sure that you learn that rule, the us and the ick acids. All righty, so now that we have a pretty good handle on compounds, at least enough to progress forward, the next thing we want to talk about is the concept of molar mass of a compound. Okay, so let's kind of, let me kind of put some things on the board. So I'm going to actually put up a bunch of different compounds. Let me just grab some out of here. Okay, compounds. Let me just put up, and I'll teach this little by little. So let me put up 4 compounds, a bunch of different types. So let me have NH3. Let me do Ca, C2H3, O2, 2. Let me go K2S. And how about, let's go H3PO4. We just saw him a second ago. All right, so we've got 4 different compounds here. Could you identify them as molecular or ionic? So let's go ahead and do, are they molecular or ionic? Let's go ahead and do that. So this one, both nonmetals, molecular. This one here, you've got a metal and then a polyatomic ion, ionic. Metal, nonmetal, ionic. All nonmetals, it's really an acid, but acids are molecular compounds. All right, so that's a little molecular or ionic thing. Now, let's ask the question, how much do these compounds weigh? So let me ask it like this. How much do these compounds weigh? Okay, one of the things that we learned about in chapter 2 was the concept of you can figure out, if you can remember the little piece of pencil lead that we talked about, pencil graphite, you can figure out how many atoms are in a sample by weighing it based on the concept of molar mass. So you can weigh a sample, figure out the grams, and then use molar mass as a conversion factor to figure out the number of moles. And from moles, you can get into the number of atoms using Avogadro's number. If that doesn't sound familiar, peek back at your notes. We did it with a little piece of pencil graphite, I believe in the second part of chapter 2. That entire concept can be applied to compounds as well. When I introduced it, we were just talking about single atoms. So let me just come back to this very simple example here. Say you have a 3-atom molecule. Let me just pretend this is H2O. I know it doesn't look anything like this, maybe like this. You know, H2O. Pretend these are both hydrogens, and that's the oxygen, okay? How much does it weigh? Well, a molecule is just the sum of the parts. So H2O would weigh as much as oxygen weighs and 2 hydrogens. And the total would just be the sum of all the parts. Does that make sense? If you're trying to weigh, you know, a total of something, you just add up all the pieces, and that would end up how much the whole thing weighs. So when we're talking about how much an NH3 molecule weighs, so a nitrogen attached to 3 hydrogens, hopefully you can understand that you would just go to your periodic table. Let me see if I can grab my periodic table. Remember that the periodic table tells us how much the atoms weigh, and you would find out how much a nitrogen atom weighs, and then you would add up 3 hydrogen atoms, and that would tell you how much the total molecule weighs. So that's one. I'm going to split this into 2 because it's really 2 ways of looking at it. That's the first thing I want to talk about, is what we call the molecular mass. The molecular mass is just the mass of a molecule. I'm not going to write that because I'm running out of space, but you could put that in your notes. The mass of a molecule is molecular mass. And really all that it is that it's just the sum of all the atomic masses. So when you go to your calculator and you take nitrogen and you find that he's 14.01, how I would enter this is 14.01, and you're going to add, plus sign, however much 3 hydrogen weighs. And so 3 hydrogen atoms. So I would use a parentheses. This is the best and fastest way to do this. Put a parentheses in there. 3 times, because there's 3 of them, 1.008. And you're using the same periodic table that I'm using here. The one from your book. That's a glare there, I'm sorry. And then close parentheses and enter. And you're getting 17.034. That would be what we call the molecular mass of this compound, 17.034. Now, what is the unit? Well, if you're talking about literally one of these, one of them, I mean, it would be impossible to isolate just one, but if you could, one of them, the unit there is AMU, atomic mass units. That's how much he would weigh. We'll just leave it at that. So that would be the molecular mass of NH3. Now, the other way to think about something's weight is not to think about how much a molecule weighs, but really frankly more often is to focus on what we call the molar mass. The molar mass, we've talked about this before, so this should be review, is how much a mole weighs. So not just one of them, but 6.022 times 10 to the 23rd of them. That's many more. That's a clump. That's a lot, okay? That would not be measured in AMUs. It would be the same number. Do you remember that molar mass and atomic mass are the same number, but the unit is different? So 17.034, but you would call it grams per mole. That's the unit for molar mass, grams per mole. We'll talk about how to use this in just a little bit, but do you remember in the previous video, I used this as a conversion factor, and I'll show you how to do that again in just a minute. So both of those are true. This is talking about how much a single molecule weighs, AMUs would be the unit, and this is focusing on how much a whole mole would weigh in grams. This is the way that you will think of it 99% of the time in chemistry, because usually chemists don't think about things one at a time. We don't do chemistry like that. We do chemistry in big batches of substances. So usually you are to think about that as molar mass. That's the more helpful one, and you'll see that most of your questions will be in molar mass. All right, let's come back to this one for a minute. There's a little bit more to talk about that I kind of skipped in a previous video. This one here is an ionic compound. Okay, so do you remember when we talked about ionic compounds, we learned that really an ionic compound exists not as just a single, this one is NaCl, but the same concept applies. It doesn't just exist as a single NaCl. It actually exists in like a whole huge crystal called a lattice structure. So the concept here is this: with an ionic compound, it is impossible to isolate or to remove just one of these green and purple units at a time. Because if you remember, the ionic bond really needs to be multidirectional. It's held together because it's attracted north, south, east, and west to the oppositely charged ion. So it's not like this is a self-existing piece. And therefore, you don't really call it a molecule. In the past, I think I've kind of called it a molecule because I didn't really want to go there yet. But with ionic compounds, which frankly is this one and this one, that's not really called a molecule because it's not a self-existing unit like this one is. This one, technically, each one is separate. Each ammonia is separate from the next guy. With these guys, it doesn't really exist like that. What you call both of these, if they're ionic, and it was in your reading, and hopefully you saw it, but you call this a formula unit. It is essentially just trying to be careful that you're not calling it a molecule because it doesn't self-exist. You couldn't really isolate it on its own. But a formula unit is basically just the smallest unit of ions that exists in the compound. Nothing to stress about, but that is the reason why for these guys, you'll have noticed in your reading, they actually don't call it molecular mass, they call it formula mass. If you're referring to an ionic compound, this number that you're adding up, they call it formula mass. To be honest, no one really cares in regular life if you accidentally call it molecular mass, or frankly, you're actually going to call them molar mass for both of them anyways, so don't make this like a hill that you die on. But I just want to explain what formula mass is. It's basically the same thing as molecular mass, but for ionic compounds, because those are not technically molecules, they're really what are called formula units. Regardless, you handle it the same way. If you're trying to figure out how much one of these weighs, you just want to add up all the atoms that exist in it. So we're going to add up how many calcium atoms. So some people have wondered about this before. That subscript applies only to the piece directly in front of it, only to the acetate ion, not to the calcium. If calcium needed a subscript, we would put it in there right there. So there's only one calcium atom. How many carbon atoms are in this whole thing? For some people, that's really easy. They can see right away that there's going to be 4, okay? Because really what this means is that you have a calcium and 2 acetate ions. So if you had to see the second one, here's the second one. Okay, that's what that means. There's one, and there's actually another one. That's what that means. So you actually have 4 carbon atoms. How many hydrogen atoms? 6. How many oxygen atoms? 4. So really what you're doing there is you are multiplying to get how many atoms of each kind that you have in this compound. So let's go ahead and figure this out together. Grab your periodic table. Don't rely on me to do it. You do it too. The best thing that you can do is learn how to enter this all in one chunk. I've seen students really try to take their time with calculating these molar masses. If you end up trying to write everything and record everything, you're just going to be spending way too much time on the simple things, so you don't have enough time for the hard things that will come later. So as quickly as you can, learn how to enter this whole thing in a string on your calculator. You'll be much better off. So calcium weighs 40.08. I'm going to add, because I'm adding up all these atoms to find out how much the whole thing weighs. I'm going to put a parentheses in here because I'm going to have to do how many hydrogens? I'm sorry, carbons. There's 4 of them. So parenthesis 4 times hydrogen. I'm sorry, I'm talking about carbon. 12.01. Close parenthesis. Plus, now we can handle the next atom, hydrogen. There are 6 of them. 6 times 1.008. Close parenthesis. Plus How many oxygens are there? There are 4. Now, oxygen is a perfect 16. So some people can do that in their head. 4 times 16 is 64. If you can do that, that'd be good. 16, 16, 32, 48, 64 is a nice something that people kind of can do quickly. So now I'm getting as an answer 158.168 AMUs for the formula mass of this guy. Now, if I want to talk about the molar mass, where I'm really dealing with how much does an entire mole weigh, it's the exact same number, but the unit is grams per mole. And notice how I'm writing it. I write it like this because that's how I'm going to end up using it in my conversions. All right, let's do a couple more. K2S. I've got 2 potassium. So with this one, I'll just enter it a little differently. Why not? I'll show you a couple different ways to do it. 2 times potassium, 39.10. And then I just press enter. This is just another way to do it. And then I'm going to add a sulfur, 32.07. And I'm getting 110.27. AMUs, if you're talking about it, it's just one of these formula units. 110.27 grams per mole if I'm talking about it as a molar mass. And the last one, phosphoric acid. So we've got 3 hydrogens. You go ahead and see if you can do it. So I got 97.994. AMUs for the molar mass, for the molecular mass, the mass of a single molecule, but grams per mole if you're talking about the mass in grams of an entire mole of them, many, many more. Okay, one thing I want you to notice is that with your molar masses, I don't want you to round these. Never round your molar masses. You'll notice that I wrote down everything that my calculator gave me. I didn't just kind of round it to 0.3 or 0.2 or whatever. And the reason is because molar mass is almost never your end goal. It's almost always a intermediate step on a larger question or a bigger problem. And in chemistry, actually in all of math and science, you're not supposed to round in intermediate steps. Okay, that's not the time to round, because what you end up doing is just introducing error and more error and more error, and then your answer is slightly off. I want you to have the satisfaction of getting the same answer as the textbook. And the only way you're going to do that is if you don't introduce a rounding error where they don't. So you never really round your molar masses. Just use the ones that your calculator gives you straight from your periodic table. Don't round even off of this. And then at the end of your answer, then you can think about how many significant figures are you allowed to report. And we talk about that more in the density lab, and it's also in chapter 1 as well. So that's really the time to think about rounding, is at the very end when you're presenting your number of sig figs. Okay, so that's how you calculate. I'm going to strictly talk about this as molar mass from here on out. Let me go ahead and now erase this part here. I'm going to keep my ammonia just for the teaching part here. So let me go ahead and now talk about how we can use this. It's going to be very similar to what we did in the chapter 2 video, but now this time using a compound rather than just an atom. Practice question. Can we calculate the number of moles in, let's just go with 1.27. Let me put a metric prefix in here. Micrograms of ammonia. Okay, so calculate the number of moles in 1.27 micrograms of ammonia. So when you are given a question in chemistry, one of the best tips that I can give people, because so many times starting is the hardest part. Where do I start? What number do I write down first? A lot of people will start just kind of randomly collecting information or whatever, and then they get a little bit confused under their own knowledge or whatever. This is what I can tell you without any exceptions. If there is one number in your word problem, or whatever you want to call it, if there's only one number, the 1.27 micrograms, that always gets written to the left. And that is where you're going to start. Many of chemistry is just dimensional analysis. So hopefully you've seen that dimensional analysis video already, the metric conversion video, that lab, online lab, because that will help you a lot with what I'm about to show you. So you've got 1.27 micrograms. Notice you have to carry the unit. The unit is completely, inextricably tied to that number. You can never drop a unit. It's like hugely important with the number. All right, so we are essentially, I want you to notice what's happening here. It's micrograms, yes, but essentially what we're doing here is what's called a gram to mole conversion, because we are given something in grams or a form of grams, and I'm being asked for the number of moles, okay? So we are being given a gram, we're being asked to do what's called a gram to mole conversion. And I just always tell students, there's this little, I don't know, device or whatever that I always write on the board. Anytime you're trying to go from grams to moles, you just use the molar mass. Just use the molar mass. Now, what is the molar mass? There it is right there. And I put parentheses around mine. You certainly don't have to do that, but it reminds me that molar mass is a conversion factor. Now, am I ready to use that right now? Remember, the whole point of conversion factors is to cancel out the units that you currently have to get the one that you want. We want moles. Now, nobody's ready yet because you have a metric prefix. We need to get rid of that micro. So how do we get rid of the micro? Well, how I do it is I always just say that in every 1 gram, there are 10 to the 6 micrograms. Did a lot of practice like that on the online lab video. So that's the first step. Now we're in grams. Now we can use our molar mass. Now, do I use it right side up? Remember, conversion factors can be always used right side up or upside down, okay? Just make sure you never, one thing some students will do by accident is flip the units, but keep the number. That 17.034, the number is with the G, always. The number is always with the grams. Never separate those two. Hopefully you see that if I use this right side up, the resulting unit will be grams squared over moles. That's a disaster. That's not what we want. We want number of moles. But if I flip it upside down and I just write it like this, 17.034 grams per mole, grams will cancel in the most beautiful way, and I will have moles as my final unit, which is exactly what I want. So now we have it set up perfectly, and now it's time for our calculator. So calculator entry, you're going to start with 1.27. Any number, and I just go left to right. I deal with one conversion factor at a time. I never gather numerators and gather denominators. Totally unnecessary and in some ways kind of dangerous because you might forget something. So just work left to right. So I'm at 1.27. I'm going to divide by 10 to the 6th. See, it's on the bottom, so I'm dividing by it. So I just literally press divide by. Now, use the second log to get the 10 to the, divided by 10 to the 6th and close parentheses. Now, in between each step of the dimensional analysis, I press enter. I let my calculator breathe. I let it record that number. I don't write it down. I just leave it in there. And then I'm going to divide again by 17.034. So this is the previous number that I had. Now I do divide by 17.034. And I'm getting a number. Now, let me show you something real quick. How many sig figs? Well, let me back up. How many sig figs are going to be in our answer? Well, this is a multiplication division problem. So you count the sig figs in all the pieces. So this guy has 3 sig figs, all non-zero digits, so they're all significant. This is an exact number. That's exactly what an exact number is, if you were wondering. It's just like a metric conversion piece. That doesn't matter. That's not a measurement, so you ignore him. And the molar mass has 5, okay? So 3 is our limiter. You pick whatever one has fewer numbers, and that's how many I get to write in my answer, 3 sig figs. Sometimes the number is super, super small, and the calculator will cut off one of your sig figs. The way this is really handy, the way to show it again. Oh, and by the way, also, do you notice that you're going to need scientific notation for this? So that's another thing too. Let me show you a little trick with this calculator in particular. If you press, your number is in there right now. If you press second DRG, you're going to see flow psi eng. Move the arrow right here over to psi and press enter, and that's going to put your answer into scientific notation. Check that out. Isn't that cool? Not only will you get your 3 sig figs back, but it will tell you the scientific notation so you don't have to think about it if you're getting confused. So the answer is 7. Now I'm getting 455. Now you only get to report 3 sig figs. That would round to 7.46 because the 5 will bump that other 5 up to 6 times 10 to the negative 8 moles, and that is the answer. Okay, so you see how that works. It makes sense that it's a small number because we started with a very small mass. Let's go ahead and do a couple more of these. Actually, you know what? Let me put that number back for a second. 7.46 times 10 to the negative 8 moles. What would have happened if this was like a part A? And what if part B had said how many molecules are in that sample? So you have to read the questions carefully. The first, part A, asked for a number of moles. So for part A, I was done. That would have been the answer. But part B is asking a different thing. Part B is saying how many molecules would be in there, like literally how many would be in that sample if you weighed it. Here, this would not be the right answer for that because it needs molecules. This is moles. It's a different thing, different unit. But if I wanted to get molecules from moles, let me show you something, another thing that I sometimes write. So there's this little cheat sheet thing here. Anytime you're going from moles to either number of atoms or number of molecules, it can be either, just depending on what you do. What I use and what you should use is Avogadro's number. That's how you go from moles to number of atoms or molecules. Now, I do it as a conversion factor. I do lots of things as conversion factors. I need to get rid of moles, so I will write it like this. In every 1 mole, there are 6.022 times 10 to the 23rd. In this case, we're talking about something that is a molecule. If it was just an atom, I would write the word atom. But this is a molecules. And now you can go to your calculator, see how mole cancels. Now take that number, preferably the unrounded number because you don't want to introduce error, times it. See, now we're timesing because this is on the top floor. Timesing it by Avogadro's number, 6.022 times 10 to the 23rd. And let me show you something real quick. You're going to put the 23rd in parentheses, but then, let me back up for a minute. Whenever I time something by Avogadro's number, or actually anything that's scientific notation, I enclose it in parentheses. See my parentheses right there? I enclose the whole thing in parentheses, and that saves some problems. So you really need 2 parentheses if you think about it. 1 to close the 23 and 1 to close the whole Avogadro's number. And I will get, for part B, 4.49 times 10 to the 16th molecules. And that also makes sense because there surely would be a lot of molecules, even if it was a small mass. Atoms are really small, so there would be a lot of them in there. Okay, so that's how you do a gram to mole, and if you're asked, a mole to number of molecules problem. Let me show you another angle on this. Maybe I'll get away from ammonia and try to just do something totally different. How about something like, let's add a couple of layers of complexity on here. So can you calculate the mass of, let's see, 375 millimoles of iron 3. How about chlorate? All right, so now we've got some layers of complexity here that we're going to have to deal with. But reasonable amount of complexity for chapter 3. All right, so what I said last time still applies. We have a math problem here, calculate. If you only have one number in the problem, just go for it, write it to the left. You're going to use dimensional analysis to do all these conversions. Now, you certainly can use algebra, you certainly can use any other, you can do these things one thing at a time or whatever. It's fine. If you get the same answer, you can do it any way you want. This is just the way I do it. I'll tell you, this is the way most chemists do it. It's also the way your book does it. It's a little bit it's kind of the most organized way because you can handle all the things you need to do in one string. And it's basically like just setting up, it's like playing dominoes. Just put the things in the right pieces, see the units cancel, and you'll know you did it right. So it's just a really nice way to do chemistry. So I'll tell you this, if you have a metric prefix, you got to get rid of it all the time. So even if you don't quite know what to do next, get rid of the metric prefix. It's got to go. How do you get rid of milli? Well, in every 1 mole, there would be 1,000 millimoles, correct? You could write 10 to the 3rd if you want, but I always just write 1,000. It's just easier for me. So that will get rid of the millimole unit. And now I would pretend I would be in moles. Now I'm not going to do it out yet. I'm going to set my whole thing up so I can just do this in one string. Now, this time, see how it says calculate the mass? By the way, mass is always grams. If you're wondering, mass, even when people say weight, they mean mass. Just use grams, 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 okay? So that's what you're trying to convert to. Your answer will have to be grams. So hopefully you see that this time you're doing a mole to gram conversion. You see that? You're doing a mole to gram conversion. And this is where I have left this up on the board. I want you to see that if you're doing a mole to gram conversion, it's actually very similar to a gram to mole conversion in how you attack it. You're still going to use molar mass. That says molar mass. Still going to use molar mass. So you need to know the molar mass of iron 3 chlorate. All right, let's go for it here. We need to know how many atoms of iron and the atoms in chlorate there are. But we need a formula. This is a name. This is a name. We need to turn this into a formula. So this is coming back to what we learned in the last video. How I would do it is just write it right above. Iron 3, what is that 3 telling you? Don't make the mistake that it's telling you something about the subscript. It's not. It is telling you the charge on the iron. So iron 3 is the Fe3+ cation. Chlorate, you just have to know by heart. Certainly, if it ends in ate or ite, you should assume it's a polyatomic ion. And chlorate was on your list of things to memorize, and that's ClO3-. And you need to know that charge to get this right. So now to get the formula, remember, this is an ionic compound. Hopefully you saw that right away. As soon as you see the metal with nonmetals over here, it's ionic. How do you get neutral? You would need 3 of these guys for every 1 of these guys, okay? Because that would get you 3 positive charges and 3 negative charges, okay? So you need, remember, this is just a 1- charge. That has nothing to do with the charge. That's just how many oxygens are in it. So this is the formula for iron 3 chlorate. Fe, enclose him in parentheses because you have 3 of these. Hopefully you can see that if we've got 1 of these, just in case there's somebody that's not feeling confident about that, I want you to see it. It's trying to get a neutral compound. Neutral meaning you have the same number of positive and negative charges. This guy gives you 3 plus charges just with one of them. These guys only give you a negative 1 charge, so you're going to need 3 of them to get the 3 negative charges to balance out him. And that's why that's the formula. All right, so we've got the formula, so that would be what you'd have to do as part of this problem, get the correct formula, so you can expect that kind of challenge on your test. And then let's get the molar mass. So the molar mass of this guy, how many irons, how many chlorines, how many oxygens? I'm going to do it myself first, see if you can do it, and then we'll compare answers. All right. Also, let me show you one more thing. I got this as an answer, but it's annoyingly in scientific notation because of what we did last time, and I had left it in scientific notation. It is better for you to not work in scientific notation all the time, because what people do is they will forget, they like won't see that, and they'll write like 3.062, and they'll kind of neglect that part just because they're not used to looking for it. So as soon as if you've done scientific notation on your calculator, go back and hit second DRG again and move it back to flow. Flow is what you want it in. Flow, I don't know what it means, but it means normal. And press enter. That's the number that I want to write down for the molar mass, 306.2. Let me just write it up here. 306.2. And so important, the molar mass is a number with a unit. What is the unit of molar mass? It's always grams per mole. And if you want to just keep it real straight in your mind, put some parentheses around it, because you're pretty much always going to use it as a conversion factor. So 306.2 grams per mole. Now that you have it, let's use it. Do we use it right side up or upside down? See, this time, because we're going from moles to grams, you're just going to use it right side up. You see how that works? The dimensional analysis, based on, you let the units do the talking. The units will kind of tell you what to do with the numbers. You don't have to memorize, oh, to go from, some people teach like, oh, to go from moles to grams, I got to multiply. And to go from grams to moles, I got to divide. But the way that I'm doing it here, you don't even have to ask, you don't have to trick yourself to memorize these things. You just let the units talk and you present it in whatever way you need to get the previous unit to cancel. So we're ready to get the answer. So let's put it in our calculators. 375. Ignore the ones. That's a waste of time to deal with ones. Divided by 1,000. Like I said, I press enter after every single section. And now times 306.2. And my answer is 114.825 grams. Now, sig figs. To be the perfect answer, remember your sig figs that you can present as your answer are limited by the number of sig figs in your input numbers and what numbers went into getting that. So this number had 3 sig figs. Those are all significant. This is an exact number. This number has 4. 3 is your determinant. So your answer, or it's the smaller of the 2 numbers, 3 and 4. So 3 is smaller, which means your answer can only have 3. So this has to be presented as 115 grams. That's the right way of answering that question. And that would be the mass of that many millimoles of this molecule. Okay, so what I just showed you how to do was a gram to mole conversion and also a mole to gram conversion. I think I'll skip on it for now, but had I presented this as a, number of molecules or formula units thing, you would have to first get it into moles before you could get it into grams. So you might have to do, oh, you know what? Let me take the time. If you already know how to do this, you can just fast forward through this problem. Let me take the time because I want to complete this concept here. So let me put another practice question up. Why not? how about, let's go calculate the mass of, I'll just make up a number, 1.5 times 10 to the 22nd. Let's go N2O4 molecules. All right. So if you want to give this a try, go for it. You can ignore me or pause the video, but let's calculate the mass, that means grams, of this many molecules. Okay, so we have one number in the problem. Now, I don't write N2O4. I just keep the basic unit, which is molecules. It really doesn't matter that you write the N2O4 there. It starts to matter when we start doing stoichiometry, like how many grams of this do you need to make how much grams of this product when you've got like two different players. But this whole question is about that type of molecule, so I don't need to kind of waste paper and write it. So I've got 1.5 times 10 to the 22nd molecules. I'm trying to convert it to grams. So I am going to end up having to do a mole to gram conversion, but I'm not in moles yet. I'm in molecules. So really what I need to do first is take it from molecules to moles. And for that, you same thing, you use Avogadro's number. But how will you write it this time? Well, you need molecules on the bottom. So you have to think to yourself, when she says Avogadro's number, what is she saying? What I'm saying is this sentence. In every 1 mole of anything, there are 6.022 times 10 to the 23rd molecules. And if that is not jumping off at you, literally write down that exact sentence. In every 1 mole, like verbally, by words, in every 1 mole, there are, that's what per means, there are 6.022 times 10 to the 23rd molecules. And molecules will cancel. And now I'm ready to go from moles to grams. All I need is the molar mass. So let's get his molar mass. Got 2 nitrogens and 4 oxygens. So his molar mass is 92.02 grams per mole. You could write that off to the side if you want, or if you're ready to just use it, that's fine too. And I will just go ahead and use that molar mass right here. 92.02 grams per mole. See how nice that is? What's really nice about this is that there's confidence that you did it right. You can see that you have successfully converted it first to moles and then to grams, and then your answer will be in grams. Now, one little thing I need to kind of warn you about here. When you enter something, see all the scientific notation stuff that we got here? You gotta be real careful. So what I would do is enter the first one, 1.5 times 10 to the, so use the second log function. And by the way, it should look like this. Sometimes people put in 10 and then another 10. It should look like that. Times 10 to the 22nd, close the parentheses. I would just press enter. Let your calculator accept the entry. I pressed enter. See how it accepted the entry? Now, are we timesing or dividing by this number? We are dividing. It's on the bottom. It's in a denominator. So you're going to press divide. Here's the thing. If you are dividing by a scientific notation, you must enclose it in parentheses. If you don't enclose the whole thing in parentheses, you're going to end up dividing by him, but then timesing that answer by that. And that's not what you're trying to do. You're trying to divide by the whole thing. So important. This is a super common mistake, but this is kind of a nice thing that I can show you on these online videos, because usually in a class, this is hard to explain. You have to enter, you have to put it within a parentheses. So parenthesis 6.022, oh, I hate that glare, times 10 to the 23rd, close the parentheses of the 23, but don't forget, you have another parentheses to close as well. And then, and by the way, if you're not talking, you can use the arrow to go peek back. It's that parenthesis right there that you're finishing. Enter. And that step took care of this step, and now I'm timesing by 92.02. And I got as an answer 2.29266. This has 2, this has 4, and this has 4. So of those numbers, 2 is the smallest number, so I only get to report 2 in my answer. So I can only say that I know for sure that there are 2.3 grams. You would round the 2.29 up to 2.3. Okie doke. That is gram to mole conversions. All right, so we're doing good, but gonna keep on moving. I made a list of everything I needed to cover. Okay, last kind of thing that we need to do is talk about mass percent and then determining into empirical formulas from experimental data. Okay, so let's do a little thing on mass percent. First of all, what is mass percent? Mass percent is an element's percentage of the total mass of a compound. All right, so that's what mass percent is. So kind of best to explain with an example. Let's go ahead and just do a practice question on mass percent. What is the mass percent of, let's say, of oxygen in acetic acid? All right, so mass percent is zeroing in on one of the elements in a compound. So acetic acid is, hopefully you memorized it, H, because that's what makes it an acid, but it contains acetate. Notice once again, the 8 became the ick. Do you notice that? 8 became ick, so that's just the rule. That's acetic acid. So mass percent is basically saying, okay, in the total mass of acetic acid, how much the whole thing weighs, like one of them, how much of that comes from oxygen atoms? That's really what mass percent is. It's just zeroing in on one of the elements and basically saying, like, what percentage of the total mass was from him. And it's just a really easy type of calculation. So to calculate a mass percent of, in this case, oxygen, we're going to do oxygen. I always think of it as 3 numbers. And then times 100. That's how I think of it. And I'm very kind of visual with my math or whatever, so I was just thinking about it like this. So this number is small, and then these two are kind of bigger. All right, so how do you do it? The first number is an integer, and what goes here is just basically the number of oxygen atoms in the compound. So the number of that atom, whatever one you're focused on, atoms in the compound. And basically, you're just looking at the compound formula and counting how many oxygen atoms there are. There are only 2 here, so you would just write a 2 right there. 2 oxygens, okay? The next number here is I just write the molar mass. It's the molar mass of the element, of whatever element your question is about. So this question is about oxygen, so you're going to write molar mass of oxygen. And the molar mass of oxygen is 16.00 grams per mole. I'm going to write it like this right now because I'm not using it as a conversion factor, so I'll just write it like that. So that's the molar mass of the element. And then on the bottom, you're going to write the molar mass of the whole compound. And that's how you're going to calculate the mass percent of something. It's pretty easy. So we need the molar mass of the whole compound. So see if you can figure out the molar mass. By the way, how many hydrogens are in here? There's actually 4. This one is written separate from those ones because when we learn about acids, you'll learn that this is the one that gets, that falls off, that gets dissociated off. And that's why they write it separately. But for now, don't worry about it. Just make sure that you count 4 hydrogens, not just 1 or not just 3. So go ahead and figure out the molar mass of this compound. Hopefully we'll get the same answer. I got 60.052 grams per mole. Now, notice the unit is going to cancel anyways, but I just like to write it in there. mass percent's not going to have a unit. Notice the only unit that was in there is gone because one's on top, one's on bottom. But let's go ahead and figure out what the answer would be. And by the way, don't forget, you have to times it by 100 because it is a percentage. So you want to times it by the whole thing by 100. So throw this into your calculator and see what you get. I got 53.29%. Oh, and yes, you want to present it as a percentage. That's the mass percent of oxygen. So it looks like there's not that many oxygens in there, but because oxygen weighs so much, his mass percent is pretty high. See, there's a lot of hydrogens, but they're so little that their mass percent would be small, kind of no matter what. So that's how you calculate a mass percent. Pretty easy, okay? Let me show you how you might end up using that. Let's think of that as, what if that was a part A? Okay, what I just had on the board, pretend that was a part A to the question. Let me follow that up with a part B. How many grams of oxygen would be in, I don't know, 15.0 grams of acetic acid? So this is just a kind of a follow-up type of question. So essentially, if you're in the lab and you had 15 grams of that whole compound, acetic acid, say you had it in a beaker or whatever, you could use that mass percent to figure out how many grams of oxygen would be in that. And honestly, all you have to do is take 53.29% of that number. Just remember that with percentages, percent means per 100. So what you would have to do is you would have to divide that by 100. You would use this number, 0.5329, to get 53% of this. Remember, 53% is about half, right? And you would times it by the whole. Notice gram is the unit and he will survive. So to get the answer to this, you would just take 53% of that total number. And I'm getting 7.99 grams, and that would be the right number of sig figs of oxygen. And that's all you have to do to use a mass percent. So there's some in-chapter questions and some questions that I'll put in from the end of chapter just to practice the concept of mass percent. But you just can calculate it and you can use it to answer kind of this type of question here. Let me go ahead and now take us to the last thing that we need to talk about in this video. And that is determining empirical formulas. So this is a term that I have not talked about yet from experimental data. Okay, determining empirical formulas. So this is kind of it's like a classic Gen Chem technique. I think they're kind of fun to do, to be honest. Let us first talk about what an empirical formula is, and then we'll talk about how to approach this. I think we'll probably just do some practice questions together, because some stuff is just the only way to teach it is to do it with practice questions, and this is a good example of that. Let me go ahead and just give you this. Empirical formulas versus molecular formulas. So empirical formulas versus molecular formulas. I'm abbreviating here. The best way to do this is through just showing you some examples. You're going to see exactly what is happening just as I do it. So molecular formulas are simply what we've been using this whole time. Molecular formulas are where the subscripts tell you the actual number of atoms in the compound. Okay, so molecular formulas are what we've been using by default the whole time. So This is the molecular formula, as you know, of ammonia, which is telling you that there's 1 nitrogen and 3 hydrogens in an ammonia molecule, okay? The empirical formula is still NH3. I'll tell you why in just a minute. There's another compound, C6H12O6, a famous compound called glucose, photosynthesis and all that stuff. That's the molecular formula because glucose truly has 6 carbons, 12 hydrogens, and 6 oxygens. That's the molecular formula. Okay, it's like the literal formula. The empirical formula for this guy is CH2O. All right, maybe you see what's happening here, but let me show you another example. This formula, H2O2, is hydrogen peroxide, just like you would have in a bathroom. Hydrogen peroxide truly has 2 hydrogens and 2 oxygens in it. But his empirical formula is HO. So can you see what an empirical formula is? An empirical formula is kind of like a reduced formula. What you're doing to get somebody's empirical formula is this one's the easiest one to see. You're dividing all the subscripts by like the greatest common factor or whatever the right word is. So like 6 goes into all these numbers, so you divide them all by 6 and you get this, CH2O. This one, the greatest common factor was 1. And so it stays the same. So if you can't reduce it, it stays the same. But this one, you can divide both of them by 2, and that turns into that. Just to check your knowledge, this was a compound I used just a little bit ago on the board, dinitrogen tetroxide. What would the empirical formula be of that? It would be NO2. Okay, so that's empiricals. Why is it reduced? Essentially, the concept here is that this formula just tells you, let me just write slash, tells you the ratio of atoms to each other. And there's some contexts where that's really helpful. For you to know which context is not really important right now, but sometimes that's really what the scientist is most interested in, is the empirical formula. So anyways, but that's what an empirical formula is. It's just telling you the ratio. Like here, there's 2 hydrogens for every 1 carbon. That's true. Okay, but it's not representing the actual numbers in the molecule. It's just telling you the ratio of 1 atom to each other. So that's empirical versus molecular formulas. Now, everything I'm about to show you on the board just is trying to figure out empirical formulas from experimental data. I'm not going to ask you to go ahead and continue on to find their molecular formulas. We'll stop with just empirical formulas from experimental data. So really there's 2 types of questions that I want you to be able to handle. The first type of question would be something, I think, let's just do a couple of problems together. I'm going to choose a couple from your book. And I'll pick evens from the back of the books or from the back of the chapter. Let's go ahead and do question number 88. It's on page 133. So it starts with a chemist decomposes samples of several compounds. Okay, so see if you can find question number 88. We'll just do question A. All right, so a chemist decomposes several samples. So they basically decomposing is just breaking down the compound into the different elements. And the masses of their constituent elements, so the elements that make up the compound, are listed. So the first type of question that you might see is where the masses are given of the different elements. And you can see that in part A, so this is question number 88A, we are given 1.245 grams of nickel and 5.381 grams of iodine. So basically, the compound that the scientists decomposed had nickel and iodine. It is nickel, yeah, nickel and iodine in it. But we don't know how many nickels, how many iodines. The question is asking us to figure out what are the subscripts in the empirical formula. So really, the compound answer is going to have nickel something, iodine something. They might be ones, they might be twos, they might be threes. It's got to be a whole number, okay, because subscripts have to be whole numbers, right? Because we learned about that in a while back. The whole goal of the question is to figure out what are the subscripts in the compound. Why did I write nickel first? Cations are always listed first, and nickel's the metal, okay? So that's why I knew it was nickel first. So if you are given the masses, here's how you want to attack this here. When you are trying to figure out the subscripts, what you can think of this, I want you to think about the subscripts as the moles of each one. The moles of nickel and the moles of iodine. That's really, the unknown subscripts is really the number of moles of each. That's maybe a little hard to grasp, but just to illustrate, do you remember, coming always back to H2O when something seems hard to understand, I always go back to H2O. Do you remember I told you that mole is like the word dozen? You're just counting. So follow me logically for a minute here. In a water molecule, there are 2 hydrogen atoms for every 1 oxygen atom, correct? Isn't it also true that if you had 2 dozen hydrogens in a sample of water, wouldn't you have 1 dozen oxygens? Isn't that true? If you had 2 dozen hydrogens in a sample of water, you would have 1 dozen oxygens. If you can say it with dozen, you can say it with mole. Just a much bigger number. So this is really the moles of each. That's a question mark, by the way. So what we want to do is figure out how many moles of nickel there are and how many moles of iodine there are. Well, can you see how easy this is going to be? We have grams. This is just a gram to mole conversion. So let's figure out grams of nickel, grams of iodine. Nickel, 58.69. And you see, we need to write it upside down because we are trying to get rid of grams. And iodine, 126.90 grams per mole. Same thing, we're trying to get rid of grams. So that tells us that we are going to have to go in and divide by the molar masses. So let's do that. 1.245. So I'm getting 0.02. Now, you can round a little bit with these. Don't be crazy, but round a little bit. So this is too many numbers to write down. So I'm going to write 0.0212 moles. And then for this one, because you don't want to introduce too much error, but you don't have to be ridiculous. So 0.0424 moles. So the first one is moles nickel, the second one is moles iodine, correct? All right, now what you do is, we're just trying to figure out the empirical formula. So go ahead and put those numbers in there. So nickel, go ahead and write that, 0.0212, and iodine, 0.0424. You just kind of transplant them, because remember we talked about the subscripts are the moles. Now, that's almost the answer, but the answer can't have, you gotta have whole numbers there. So what you do is you divide by the smaller of the 2 numbers. Now you have to just make sure whatever you do to one, you do to the other. So I'm just gonna pick the smaller of the 2 numbers. That's 0.0212. What that does is essentially fixes one of them. One of them will become a 1. So nickel now is a 1, and iodine, I can see, is a 2. And that is the answer. Ni2. Alrighty, that's the first type of question. So if you're just given masses, it's very easy. Get the moles, transplant the moles as the subscripts, divide by the smallest to turn them into whole numbers. Not too bad. Let's go ahead and show you the second type of question that you might encounter, and then we're going to be done with this video. The second type of question would be when percentages are given of the 2 elements. And as an example, let's do one together from the back of this chapter. I'm going to pick question number 90. Let's go ahead and do 90B together. So this one says calculate the empirical formula for each natural flavor based on its elemental mass percent composition. So really these are just mass percents like we calculated before. B wants us to kind of figure out vanillin. So this would be the chemical compound in vanilla. Cool. It's going to be an organic compound. All those good smelling compounds are always going to be organic compounds. So vanillin, and vanillin contains 63.15% carbon, 9.87% hydrogen. Nope, I'm writing the wrong thing. My bad. 63.15 was correct, but hydrogen is 5.30%. And oxygen is 31.55%. So see, with these ones, we're given the percentages of each element. And notice, folks, that it's going to add up to 100 because the only three elements that you have are CH and O, or else they would have told you about a third one, another one. And it's a percentage, so you're just kind of divvying it up amongst the species. So it's got to add up to 100, and you can see visually that this will add up to 100. All right, so how do you do this type of problem? At the end of the day, it kind of starts out the same way. Let me write it right here. You're going to need to figure out, and by the way, these organic compounds are kind of always in the same form of glucose, like C, then H, then O. So that's why I'm writing it in this order. You need to essentially figure out the moles of him, the moles of him, and the moles of him. But how can we do that from mass percentages? The way that this works is this. It's easier than it sounds, but first let me explain it. The way you want to think about it is you want to just pretend that you have, just think about, even though they don't tell you it, just pretend that you have a 100-gram sample. You can like think about just like this hypothetical sample that weighs 100 grams. If the whole sample weighs 100 grams and 63.15% of it is carbon, then there would be 63.15 grams of carbon in the sample, correct? Because if you're this is like an imaginary sample, but it's a good way of making this easier on yourself. Hypothetically think of a 100-gram sample and then just divvy them up correctly. So 63.15 grams would be carbon, 53.0 grams, or sorry, 5.30 grams would be hydrogen, and this oxygen would be 31.55 grams. Really what I did is, and this is why I'm saying it's kind of easier, if you're given percentages, literally just write them as grams. It's easier than it seems. Literally cross out the percentages just like I did here and turn it into grams, because you're basically just operating from this point of view of a hypothetical 100-gram sample. All right, that's really how this works. And now it's going to look exactly the same as the previous one. So let's see what we can do here. Let's handle carbon first. Carbon is 63.15 grams. Let's figure out his moles. 12.01 grams per mole. You'll notice I've got some of these molar mass memorized. Some of them are so common that you'll have them memorized in no time. You're just going to use them kind of a lot. So let's figure out how many moles that is. 5, and once again, don't round too much, so 5.258 moles of carbon. Make sure you keep track of who you're talking about, or else you're going to get yourself into some messy situations. So let's now move on to hydrogen. 5.30 grams of hydrogen. His molar mass is 1.08 grams per mole. .258 moles of hydrogen, and and oxygen. 31.55 grams, and oxygen is 16.00 grams per mole. Notice one possible error is for folks to think, oh, oxygen and hydrogen for that matter, they're diatomic elements, so I need to times it by 2. For these types of problems, that's not how you want to think about it, because this is really talking about the percentage of that type of atom. It's not talking about the species oxygen or the species hydrogen. So for this one, don't get pulled, don't do anything with the diatomic, just pull oxygen's molar mass straight from your periodic table. So I'm dividing it by 16, and that is 1.97 moles of oxygen. Now take those numbers, put them where they go, and we are almost done. Carbon, hydrogen, oxygen. So carbon was 5.258, hydrogen 5.258, and oxygen 1.97. So we are going to divide by the smallest of the numbers. In that case, that's oxygen. Let's see where that leaves us. 5.258 divided by 1.97. Okay. Actually, I wanted one that did this because we want to make sure that we can handle this. So I'm getting carbon 2.67. It's really 669, but let's go 2.67. Hydrogen is also 2.67, and oxygen is 1. So sometimes, like the previous one, you just do this first thing and you're done because they all landed on a whole number. Like in the previous one, the other one landed on a 2, or really close to a whole number. Like it can be 0.99, that's fine too. But this is not close to a whole number, and you can't just round it willy-nilly. However, it will be a number that you can multiply by some other number to get a whole number. So you kind of have to do a little bit of guess and check here, but let's take 2.67. If I multiply it by 2, does that land me on a whole number? No. Let me try multiplying it by 3. Ah, it does now. Do you see how, and really what you have to do, remember, if you multiply any of these, because it's ratios, it's empirical formulas, you have to multiply all of them by that. This, you have to basically figure out what number do you have to multiply them all by to get everybody a whole number, because everybody has to be a whole number in the answer. So I just try 2 and then 3 and then 4 until I get a whole number. When I times it by 3, it's basically a whole number, 8.01. So that tells me that this answer is C8H8O3. That is vanillin. Now, I'm going to end the video here and then I'm going to go check to make sure it was vanillin. Google vanillin. Hopefully it's C8H8O3. But that should be the answer. Okay, so that's empirical formula from percentages. That's it. We're done with chapter 3. Thank you for your attention. Good job and good luck working on all this stuff.